Hi, everybody. Welcome to the LDC Institute. This is actually our first institute in our updated conference room, so it's very exciting. We're live streaming also on our YouTube channel for LDC staffers working remotely. So to facilitate that, Kyle is wearing a mic, and when question time comes around, I'll bring the mic around as well, so we can work for a maybe a little better sound quality. So we're very happy to have Kyle Gorman with us today. I think many of you know Kyle since he got his PhD here. So I know that he's happy to be back and seeing a lot of old friends. The topic of his talk is a tutorial on finite-state text processing. And I, for one, really want to understand what this is once and for all. Kyle is currently assistant professor of linguistics at the Graduate Center in City University of New York and director of the master's program there in computational linguistics. And he also works as a software engineer in Google Research. So we're very happy to have Kyle. Please welcome him to the Institute.
Well, thank you very much for having me. Today I'm demoing some entirely new presentation software and slide building software. So apologies if there's any snafus there. We'll see how that goes. I'm hoping to, this is the first time I've taught like a sort of a longer tutorial on this topic, and I'm hoping to sort of continue to expand it. And at the end of this presentation, or perhaps on the way home, I'll try to create a permanent, easy to find URL for this tutorial, which I'll be periodically updating. A handful of you perhaps will be going to the LSA meeting, Linguistic Society meeting in New Orleans in January. A sister society called SKILL, the Society for Computation and Linguistics, will be holding a series of workshops, and I'll probably be giving an expanded version of this once I figure out exactly how this darn presentation software works. Also, since we have plenty of time, please feel free to cut in if you'd like to interject, raise questions, etc. This is quite a bit of this is a sort of a high-level view of the topic, and if we can go into detail later. Also, I think I'm trying to sort of develop a user community around these tools to the best of my ability. So if you contact me about issues with the tools, I'd be glad to take them up with you. So today I'll talk to give you a bit of formal preliminaries to FSTs, finite-state transducers. I've come to believe that these things are actually pretty much anyone can learn the basic ideas of how these things work. There's a lot of complexities, but they sort of allow you, they're really interesting tools. As like sort of a software engineer, they create sort of new class of failure modes for you. If you're building an RNN neural network, your failure mode is probably non-conformant array sizes or something like that, right? If you're a sort of classic machine learning person, it just doesn't converge. In FST land, the errors take a different form of sort of composition failures and things like that, all kinds of new, interesting types of things to deal with. So I'd like to give you some background there. I'll talk, I think, a bit more about OpenFst and friends. OpenFst is the core set of libraries, and its friends are the things we use to actually build finite-state transducer applications. I'd like to just very briefly about sort of what's available in the past and what's available in the future. I think this is actually pretty important. Even if you know all the algorithms, there's like a lot of software knowledge you need as well. I'll talk just a handful of key FST algorithms, including some sort of lore in the field. And I have 2 or 3 worked examples I can show you as well. So, formal preliminaries. So the idea of state machines and automata are very, very old idea. There's clear precedents that sort of predate even digital computing, as we understand it. There's quite a bit of work before World War II, for instance, on this topic, on the subject of the halting problem and things like that. A lot of that stuff was conceptualized in terms of these, what we call state machines. And so what's a state machine? Well, we all know this kind of state machine. Traditionally, people use the old coin-operated turnstiles. And in New York, no one under 40 even remembers those, so I don't bother, but I know you still have the... I have used tokens in the Philly SEPTA system.
Not anymore.
Not anymore? Okay, I used one like a year or 2 ago, but I had to like go to a special gate, and the person just let me in. So Basically, I don't think I actually used it. I think they just took my token and separately let me in for free.
The system's not working yet. It's there.
Oh, okay. So, but we all know, we've all seen the old-fashioned gumball machine. The gumball machine is a hardware example of a state machine, which demonstrates, I think, that this goes beyond sort of mathematical or software conceptions. Also, these things exist in the hardware world independently of digital computing or independently of algebraic formalisms. A gumball machine is a state machine because its operations can be described in terms of a fixed, finite, as it happens, set of states and transitions between those states. Gumball machines, I like to argue, have at most 1 bit of memory, and that's expressed by the fact that they have multiple, that this machine has, in fact, 2 states. Gumball machines, what do they remember? Well, they remember whether there's a coin sitting right there in the slot, right? That's something that the gumball machine, you can think of that as sort of the 1 bit of information the gumball machine knows about itself, as it were. So we can describe the operations of this machine as follows. I know in the current state, as depicted, there's no coin in the slot. So if I turn this knob, nothing happens. You can think of that as I can sort of do a self-transition. I can sort of attempt and fail to change the state of the machine. Another way I can change the state of the machine is I can actually insert a coin into the slot. Put it down here like that. When you do that, you sort of change the state of the machine in some meaningful way. The next thing you can do is you can then, when the coin is in the slot and you turn the knob, you get a gumball back. You then return into the initial state depicted here. And you can do this as many times as there are gumballs. Let's assume that this is actually an infinite gumball machine. For sake of argument, it's a lot easier to model than a gumball machine with a finite amount of it. Or just imagine that the shopkeeper always comes by and fills it up for us. So this is a familiar state machine we've all seen before. It turns out that this notion of a state machine is incredibly useful, particularly in basically modeling linguistic systems, because of the essentially sequential nature of language as we experience it. The externalizations of language are inherently sequential. This is like one of the puzzles of language as cognitive science is how is it that we conceptualize of language as having these logical relations and hierarchical representations, yet whether we sign or we speak or we write, we have to basically take the signal and linearize it. Take all those representations and linearize it. This makes it very useful. This makes these sort of state machines, which are very good at modeling sequences, useful for our purposes. So I want to give you a couple formal preliminaries, many of you will already be sort of familiar with these basics. Let's just remind ourselves what a set is in the mathematical sense, mathematical logical sense. A set is an abstract, unordered collection of distinct objects. And these objects are called the members of that set. I say distinct because we usually assume that the sets can't contain duplicates, or that we don't store any information about how many instances we put into the set. By convention, we use capital italic letters to denote a set, and we use lowercase letters to denote their members. Set membership is indicated with this little member of symbol /in in LaTeX. So we read this like little x is a member of big X. We also occasionally need the empty set notation, which is here. The first class of finite machines we'll talk about are the so-called finite-state acceptors, or FSAs. The FSAs model sets. Well, not just any type of set, though. We also need to talk about the subset relation. The set X is said to be the subset of another set Y, just in case that every member of X is also a member of Y. The subset relationship is only with this is the subset system symbol here. You have this little underline, so this is like this includes the so-called improper subset where they just happen to be the same set. That's right, it's X is a subset of Y. We need a handful more logical operations. Let's introduce them. The union of two sets, X cup Y, is the set that just contains those elements which are members of X, Y, or both. So, and this is the sort of so-called intentional notation here, as opposed to listing within these things. It says X is a member of this union if it's in both members. If it's either in X, Y, or both. Big X, big Y, or both. Similarly, intersection is related to logical intersection. X cap Y is a set that contains just those elements which are members of both X and Y. So in intentional notation here, the intersection of X and Y is X, means little x is in X and little x is in Y. That's really it. our sets in finite state land will not just be any kinds of sets, they'll be sets of strings. Strings are sort of require some special notation here. We first off imagine, in anything I'll talk about today, that we have some kind of finite alphabet, which we'll denote with capital S sigma. And sigma will be a finite set of symbols. So really, what are those symbols? Well, it depends on our application. In speech applications, they might be phonemes. They might be so-called context-dependent phones, something like an A preceded by a B and followed by a D. That's a common notation we use in these things. It might also be a diphone. It might be like the transition from a B to an A. That's a notation we use in traditional text-to-speech synthesis. If we're processing characters, it might be, well, bytes, essentially. Or if we're processing Unicode code points, we can enumerate the set of Unicode code points we care about and use those as our symbols. We also have words. Words or tokens are also perfectly good things that can be defined in our alphabet. We'll say that a string, or perhaps a word, somewhat imprecisely, is any finite ordered sequence of symbols from sigma, such that each symbol is a member of sigma. And by convention, I'll use sort of like typewriter text if necessary to denote these strings. The empty string, we also have a special notation. The empty string is denoted by this Greek letter called epsilon. Yes, it looks a lot like the euro symbol. That's not an accident. By convention, that is the empty string. Perhaps because it sounds like the word empty. The word, it also means, epsilon means bald in Greek. So it's actually like, or stripped bare, as it were. So that's a helpful notation there. String sets are also, sets of strings are also sometimes known as languages, somewhat imprecisely. Languages in the formal language theory sense. I don't want to claim that these correspond to either common sense or linguistic notions of what a language actually is. This is probably familiar to most of you. There's two sort of special operations I can do with strings or string sets. So I can define these over either individual strings or individual strings, or perhaps we call singleton languages, sets that contain only one string. Or I can define these over arbitrarily large sets as well. The concatenation of two languages, which we'll just write x, y, for x and y, consists of all strings formed by, well, concatenating the strings. So if x is the set cat and y is the set dog, then their concatenation is cat dog, just written like that. And so this is just once again the intentional notation for that. So that has a common sense notation. I'm allowed to just concatenate strings or sets of strings in sort of obvious way. We also have a notion of closure. This term is so desperately overloaded in the sort of formal computer science world, the formal languages world, and the computer science world. It means about 10 different things. The closure I'm talking about here is what might be called the concatenative closure. So in the sense that if I can concatenate I can concatenate a set with itself. I can do that 0 times, 1 time, 2 times, n times, on and on and on and on. If you can just do that an infinite time, it can be said it's closed under concatenation. But in the formal language world, we just usually call this operation closure, and we write it x superscript star by convention. And that's a infinite language, and it consists of 0 or more what you might call self-concatenations of x with itself. So sometimes you write this as x of 1 is just x. X to the superscript 2 means x concatenated with itself. So every string in x concatenated with every string in x. This is that 3 times. So every string in x concatenated with every string in x concatenated with every string in x, and so on and so forth, indefinitely. Also, we have the special empty string right there. And we can write this as this is just another way to sort of write this all out. This is very useful because we often need to sort of define not merely the vocabulary for our task, the alphabet sigma, but we often need to define the closure for that, because we often compute interesting complex operations over that closure. We say something like, we want all the possible strings in our language but the following ones. And so it's often hard to talk about infinitudes in software terms. You can't materialize an infinitude. Actually, but you kind of can in FSA land. We can take a finite machines can allow us to build a very small object which contains all the strings in a set. even though that set is, in some sense, infinite. So one of the motivating things for the use of finite automata in language studies is the notion of regular languages. This was famously defined by mathematician Stephen Kline. I'm not actually sure if there's some dispute about what's the best way to say his name. He's American, as it happens. In a 1951 tech report from the Rand Corporation, which was later published in 1956 in a book edited by John McCarthy, the famous computer scientist, and Claude Shannon, as it happens. So good team of editors right there. The inventor of AI and the inventor of information theory edited the seminal paper. It's the first paper in the volume. And Kline was interested in defining a useful set of formal languages which might correspond to interesting linguistic realities. In fact, his paper is entitled something to the effect of like comparing automata notions of language to so-called nerve net representations of language. He was actually interested in a question that was very hot right now: how do finite automata relate to neural networks? Of course, the neural networks of 1951 were rather primitive compared to today's, but he was already on a terminal question. So in an attempt to formalize this, he defined what he calls the regular languages. Obviously, there's nothing normative intended when I say regular language. It's just simply a well-defined class, and that is the denotation he chose. That's the term he chose for that. There's nothing. I don't mean to say that they're good languages or anything of that sort. It's actually very easy to define what they are, given the notations we just developed. That fits in a slide, and not even a particularly dense one. First off, there is something called the empty language, which is just an empty set. That itself is defined to be a regular language by fiat. Secondly, the so-called empty string language, which is the language which contains exactly one string which is empty, is a regular language. Neither of these are useful for really much of anything, but they're part of the definition. If S is some symbol in the alphabet for our task, sigma, then the so-called singleton language is itself also a regular language. So I'm basically allowed to take every element from my alphabet and make a language out of that. So these are all things, each one, so this is a regular language, this is a regular language. All things that satisfy this definition in your alphabet for your task are also a regular language. So these are finite so far. Here's where the infinitudes begin. If X is a regular language, then its closure, X star is a regular language too. So I'm allowed to sort of use the concatenative closure of a regular language is itself a regular language. So as you might expect, it turns out that we say that regular languages are closed under this concatenative closure operation. That is to say, every one of them is also a regular language. And also, we have ways to combine two regular languages. If X and Y are both regular languages, then we're allowed to concatenate them, get a new regular language, or we can compute their union. We also get a new regular language. He doesn't mention intersection, but that's also, that works too. You don't need to, actually, in this definition. And everything else that can be derived using these steps is not a regular language. This is a key definition that turns out to be incredibly useful. But it was almost immediately hit with bad negative results, or so you might think. These all happened, So the Kline defined these in 1951. The paper was circulated in 1956. And I think they were popularized in part not just by that one particular paper, though it was probably influential, but also by their discussion in the context of the so-called Chomsky hierarchy, or Chomsky-Schutenberg hierarchy. Yes?
It's actually important that even before Pynini got into the act, there you had the information theoretic work, Claude Shannon, talking about Markov chains, which are kind of a stochastic version.
Yeah.
Defined slightly differently of regular languages.
Yeah, certainly that's like one touch on much to say today about, but
That was 1948.
right. I mean, yeah, Shannon was a key. Well, he published that paper by Kline, for instance. So yeah, there's clearly some strong connections there, both to the sort of older vanguard of information theory thinking, and also this newer vanguard of the classic AI thinking. Were both sort of present in this work. I think a lot of people come about this because they learned about the Chomsky hierarchy, and then this is a sort of base element when you learn the Chomsky hierarchy traditionally. And you know, I couldn't even decide which papers talk about this. But one is classic, the Chomsky and Miller paper, of course, is a classic paper on the topic. Not long afterwards, this was followed by two seemingly negative results. Results that you might take as discouraging for this one. First one is an observation made first informally and then several times formally later on, is that what we might call traditional phrase structure grammars, the ones that basically people had been using up until the point where transformational grammar emerged, belong to a higher class of languages, the so-called context-free languages. And these transformational operations, it's not surprising that these transformational operations even rise to a higher class than these phrase structure grammars. So we know these to be insufficient, basically, for describing context-free grammars are clearly insufficient for describing human languages. And even they are much higher in this hierarchy of language types than the regular languages. This point was made informally in a series paper by Chomsky, Miller, and Schitzenberger. All had these points. Actually, it was proved a bit later that this notion of the pumping lemma had to be generalized for regular languages for that proof to be accomplished. And so the proof is the classic proof is a bit obscure. But that's already a bad idea. So, like, human language is not going to fit in the regular languages. It's already clear as a general purpose observation. The other observation is the famous, is what's called Gold's theorem traditionally. Gold defines a notion he calls language identification in the limit. This is a framework for what does it mean to learn a language, learn a formal language from data. And in his framework, framework is relatively adversarial in how it's defined. It makes it hard to learn a language. Like the system is sort of independent of like data presentation, so you can have arbitrarily bad data order. Like I can come up with an adversarially better. Malicious, yeah, absolutely. It's a very strong definition of what learning is. You're not allowed to like get the data in good order. Like it might be easier to sort of get easy sentences and then hard sentences. You can't do that.
Well, and in particular, I think the result really loses most of its interest when you realize that it depends on the fact that a malicious teacher could actually withhold the fact that certain sentences of a certain length will now work in a completely different way from what it's doing. They can withhold that information
Arbitrarily long,
and then when it comes up, gosh, you're in the wrong language.
Yeah. And it's very easy to sort of, in fact, if you've read the Gold paper, it's difficult, but it's really, it becomes easy to sort of design counterexamples, like of the form that Network is talking about. You can just always show the n+1 example, right, and that can defeat the learning. So this was an extremely influential result, as far as I can tell, in the field, and sort of discouraged a lot of, I don't know, sort of maybe utopian thinking about how information theory is related to cybernetics, related to AI, was going to relate to cognitive science of language.
I think it's puzzling, actually, and too bad how influential it's been.
Absolutely.
Not long after that, some other results that show that under extremely weak assumptions about the non-maliciousness of the teacher, in fact, languages several steps up in the hierarchy are learnable within epsilon.
Right. So you can back up to slightly less malicious settings, and you can also allow, there's a lot of work on so-called the query language learning, where you're actually allowed to ask, okay, but what about this one? And if you're allowed to do, a very small number of those, you can get a much tighter bounds and these sort of things. But that work developed in the 80s. Really, it took about 15 years before that actually people started sort of returning to this question in great detail because of that negative result. I sort of fast forward through the 80s to the last 10 years, though. It turns out, though, that an enormous amount of linguistically interesting phenomena can be described in terms of regular languages, or the special case which we'll talk about in a second called the regular relations. Regular relations generalizes, so instead of just talking about sets of strings, we're actually mapping between sets of strings. We're doing transductions. An enormous amount of interesting phenomena can be described in these terms, despite the fact that phrase structure grammar is not one of those things, despite the fact that arbitrary syntactic displacements are not one of those things, despite the fact that you cannot, in this malicious setting, be guaranteed to learn the language. Despite that, we still have really good results. So an example of this is in my colleague Richard Sprode has a book from 2000. He has a lot of books. One of his books is it's called Computational Theory of Writing Systems. And in this book, he proposes that, practically speaking, the mapping between basically graphemic form and phonemic form is regular in all languages of the world. And he attempts to sort of adduce counterexamples, and the closest he gets is the way that Malagasy numbers work. Malagasy is spoken in Madagascar. The numbers are sort of it's sort of a mirror image of English, how it works as it happens. So if you want to say like let's say you want to say 1969, you actually say 9 and 60 and 900 and 1,000, more or less. So if you want to sort of map the digit form of that, as we write it in English, to the way it's spoken in Malagasy, that is not regular. You can quickly demonstrate that fact because it's a reversal of the actual string you want. That's the only example he's able to come up with in hundreds of writing systems. What does a company like Google do with Malagasy? We pre-process the string with C++, input it to a finite-state machine that takes care of things, and then undo that reversal at the end. Sort of things are like basically trivially adversarial examples as opposed to interestingly adversarial ones. That's just one example that has been noted years and years ago. In the actual like sort of both the communities of sort of computational linguistics and this community of so-called grammatical inference community, people who study what is in fact learnable of informal languages, we have an incredible number of positive results actually about provably learnable subsets of regular languages. Some of these are proved with respect to Gold's definition. Some of them are actually proved with respect to even slightly more adversarial definition from Kyle and Gorman, which is sort of like a generalized Gold but even worse. So for instance, Hines shows that like so-called long-distance phonotactic patterns are trivially learnable. In fact, I can write it in 20 lines of Pynini. The algorithm that's described here, and Rogers generalizes that. What else can we tell you about some of these results here? A lot of these things generalize to arbitrarily complex, like phonological rules, interactions of the phonological rules, including the so-called opaque patterns. Chanley et al. Showed that these basically all opaque patterns can be described that we know of can be described as provably learnable subsets of the regular languages. These families are called the subregular languages, and respectively the subregular relations, or sometimes the subsequential functions. All of these things, basically all of phonology, as far as you can tell, modulo full reduplication falls under the subset. So that's a surprising result, actually, and it's been quite a bit of work. And I think people like Jeff and Jim Rogers and Jane and Adam really had to fight uphill to get linguists to care about it. Also, it's really interesting work because it sort of generalizes our understanding of what the rules versus constraints. These proofs don't really care. It doesn't really matter. We don't actually talk about the internal mechanisms. We just talk about the input-output mappings and how hard they are to learn. And the answer is almost all of them are provably learnable. But it took a long time to get from results like the Gold theorem and the pumping lemma for regular languages and context-free languages to actually show that these technologies are going to be useful for arbitrary linguistic problems. In the meantime, though, at Bell Labs and later AT&T and Google and places like that, people were simply ignoring these results and focusing on what could actually be built. So we have some formalisms. Having told you about these, about strings and sets, let's use these terms to describe a simple type of machine that actually recognizes or parses or accepts regular languages of arbitrary complexity. One of the results of Klini's work is that the so-called that all regular languages can be recognized by some so-called finite-state acceptor, and conversely, all finite-state acceptors correspond to at least one regular language. That is a result from the 50s. The formalization I use here is borrowed from my colleague Mario Mori, who is sort of the world's foremost expert on these in 2019, I would say. Here's how he defines a finite-state acceptor, a device which recognizes any regular language. We have a set of states, which we'll call capital Q. We have an initial state, or sometimes called start state. I use those interchangeably. S in Q. It's just going to be one of the elements we'll have arbitrarily defined to be a start state. Some formalizations allow you arbitrarily many start states. I'll just, for algorithmic reasons, always say there's exactly one. A set of final states, which we'll call capital F, which is a subset of Q. Once again, some implementations require that there be exactly one final state. Algorithmically, we find it much easier to have a lot of final states. So we allow arbitrarily many of them. Also, we need to define some alphabet over which the acceptor works, which we'll call sigma. And finally, this is the sort of mysterious thing, is we'll have a transition relation, which we'll call a little delta. And that'll be a relation that maps from, you give it a state, and you give it a label, or epsilon. Epsilon is magic. And it maps you onto another state in Q. So this is a transition relation because it tells you for any, you're at state 1, and you see label epsilon, where do you get to go? It's a relation because there can be multiple options in so-called non-deterministic finite acceptors. Here's a little more definition I need to give you. What does it mean for the machine to accept something? Well, let's just extend delta so it sort of like uses an obvious sort of recurrence. So instead of delta just taking a single state and a single label, now it can take strings. So what this says basically is if I'm at some state and I have some string and I get one more symbol from that string, then I'm allowed to say whatever from Q to W takes me, Q to WA is the next step, basically. So this is now I can actually input a whole string as opposed to a single symbol and get my answer out. So what does it mean to say that we accept a string? Well, if the string is in the vocabulary, it's in sigma star. It's accepted by the machine just in case that if I start from the start state, S, and I give it the string, I end up in a final state. So to accept a string means that I began at the start state. I'm allowed every transition in that of every symbol in that string takes me to another state. I don't get lost, and I end up in a final state. Here is a famous regular language and its corresponding transducer. The regular language here is M, O, and then we'll say M-O-O, and then O star. So this is sometimes called the cow language because it says M-O-O-O, M-O-O-O-O, M-O-O-O-O, etc. You have to have at least 2 O's, but you can have more. So does this accept mu, M-O-O? Well, yes. The answer is I begin at the start state 0. By convention, the start state's a little bit darker. I'm not sure if it comes across, but this is a little bit darker, thicker line here. There's exactly one start state, and in this case, it's 0. The numbering doesn't mean anything. It's entirely arbitrary. So I could have reversely numbered this, and it would be the same machine as far as we're concerned. We begin at 0, which is one of the valid states, the start state. Now, imagine the string is M-O-O. Well, I'm allowed to take a transition from 0 to 1, matching M. Okay. Now the next thing when I'm reading my string is an O. I'm allowed to take a transition from 1 to 2. Okay. Finally, I have one more O. I'm allowed to take a transition from 2 to 3. The string is now exhausted, so I can't take any more transitions. The question is, am I at a final state? The final states here are indicated with the double circle, and the answer is yes. Now, if it happens to be that there's one more O, I'd be allowed to take a self-transition, as we call it. So I sort of go from 3 to itself. That is permitted. These are sometimes called self-transitions. Once again, I would be at a final state. If I want another 0, I'm allowed to do that, so on and so forth. This is sort of the essence of what it means to match. So we say that M-O-O is a valid path in this machine, M-O-O-O-O is a valid path, and so on and so forth. Everyone good so far? In many cases, though, we're not interested in sets of strings so much as relations or functions between sets of strings. Let's define a very simple sort of relation between sets of strings, and I'm going to do this somewhat in a novel way. You may be familiar with the cross product operation in set land. The cross product of two languages, x cross y, that's a cross, not an x there, is one such relation. It maps, I'll say, any string in x onto any string in y. And I'll write this with a little mapping symbol here, as opposed to, I don't know what else to put there, but we'll call this maps2. And so this says x cross y contains every pair of x onto every pair of y, or every little x in x onto every little y in y. So this is sort of if I just have two sets, this just enumerate, allows every element in the first set to map to every element in the second set. Subsets of this cross product of two regular languages are known as the regular relations, or sometimes called the rational relations as well. Those terms are interchangeable and are very useful for us. So we can define a machine called the finite-state transducer. That's very similar to what we just did, but also can perform this mapping. The way I've done it is borrowed from Mori, but there's many such ways. Let me just walk you through this very quickly. We say that this FST, a finite-state transducer, is a 7-tuple. We've seen the set of states before. We've seen the initial and final states as before. We've also seen the input alphabet. Now I also have an alphabet. I've called this the input alphabet. Separately, we have the output alphabet, capital delta. These can be identical. It doesn't matter, actually. Sometimes they're defined as such. So then we also have a transition relation as before. This is the same one you just saw before. So this actually goes, we give it a state, we give it a label or epsilon in the input alphabet, and it gives us a new state. So this allows us to walk through the machine. The way that Mori defines it here is that we also have something called an output relation, which we'll call a little sigma. And once again, you give it a state and a label from the input vocabulary, and it gives you a string on the output vocabulary. And one way to define this is it can give you arbitrarily long strings, or it can give you a single element. Like it can give you a single element of capital delta, or arbitrarily long one of capital delta. Actually, it turns out these machines are equivalent. There's a obvious homomorphism between the two. So once again, we can sort of extend this output relation using the same class of recurrence I used before. Basically, I basically say I'm allowed to sort of like concatenate all the output strings to get the actual final output string. That's all this really says. And so we say a string W is transduced in the case that we start at the start state, we give it the word, and we end up in the final state, a final state. And in this case, the output is given by this output function here, which is sigma s of W. So we say that, in this case, we say that W maps onto whatever that gives us, starting at the start state. And that is just one of many ways to define these things. There's one last detail, which I'm going to skip because it's already pretty far in here, which deals with weights. Final extension of these machines is to so-called weighted finite-state transducers, or WFSTs. In this model, each transition is associated with a weight, as are final states themselves. And the requirement is actually that to make these things coherent, weights can be basically an arbitrary type in the world, so long as we define a set of the weights, which can be infinite, can be at the real numbers, or integers, or something like that. And we also need to define two operations subject to the definitions of what's called a semi-ring. If those of you who are familiar with abstract algebra will know rings. A semi-ring doesn't necessarily have a subtraction operation. So what we need to do is we need to define how do I combine two weights? Like how do I multiply them essentially? Like if they're probabilities, you could just multiply them, for instance. You could say multiply. And also, how do I add them? And that adding and multiplication has to distribute over addition. And everything has to be approximately closed. That's basically the only requirements. In practical terms, what we often do is we first have, these weights are basically probabilities. So then we multiply at every step For every transition we take, we multiply the weight from the previous one. So we just have a big product. And addition we can add, once again, if you want to. Or we can also take the max, depending on what we're doing. These are both logical possibilities. In practice, those of you who have done computing where you're using lots and lots and lots of small probabilities know that you encounter this phenomenon known as underflow. If you multiply a ton of small probabilities together, they just become 0. That's a very common problem. So one way to get around this is instead of using actual real probabilities, we use negative log probabilities. This is, and then instead of multiplying, we add. So when the logical multiplication is in fact an addition. That solves an enormous number of problems, and that is sometimes called the tropical semi-ring. And another variant of it is called the log semi-ring. Exactly how these work is, I feel like, out of the scope of the amount of time I've been allotted, the amount of time I'm willing to talk in one day. But I'm glad to take questions about this and how they're handled in our libraries. That brings me to software. That's, yay. Yeah.
Did you say anything about epsilon transitions yet, or you just?
I haven't yet. What do they do in a path? Let's say. So.
Always take that for an example.
I suppose I have. I can tell you things about this. So in my definition of like what the output relation does. So what happens when you concatenate an epsilon with something? Let's just say that's a identity. Epsilon is the concatenation identity, we can say. So that's basically fine. That works for an enormous number of problems. The one place where that becomes interesting is algorithms which don't know about epsilons. If we apply certain like optimization algorithms, don't really understand that epsilon is magic, and that it doesn't actually change the path. So we have to deal with that. I talk about that just a minute in this optimization section here a little bit later. Like how do we optimize MFST in our libraries? Yeah. So like. The algorithms that extract paths are epsilon sensitive. They understand that epsilon is special. The algorithms that we use to remove epsilons or move epsilons around in the machine understand epsilons, but we assume basically every other algorithm we use doesn't know that epsilon is magic. You also can define a class of transducers called the E-free transducers, traditionally epsilon-free transducers. We just say that actually, for instance, that actually no, it's sigma, or it's sigma, not sigma union epsilon. We just say that there's no epsilons. They don't exist. You have to handle them. That's fine, too. That's a logical possibility. Let me tell you a little bit about the tools available. Well, begins here with the two ancient forebears. The first one is the so-called Xerox toolkit developed at, I believe, at Xerox PARC. It's sometimes known as XFST. The sort of last... The last use of this is the Beasley and Cartoonin book about it. I think sadly, they wrote that book about 10 years too late. This doesn't have a normal modern software license, so it's not easy to use in core software. It came with a lot of interesting stuff. It actually has tools to help you sort of do grammar compilation operations in it. And it actually defines its own interesting domain-specific language to sort of write grammar rules and combine them. And so actually it's a little bit complicated because it's a tool, but it's also like a interactive command line thing, and it has a stack of the rules. It gets very complicated very quickly. The major limitation of that is that only a handful of useful algorithms for which are defined over FSTs are actually implemented. So for instance, there's no generic way to optimize the machines in that library. Something we can provide and I talk about a little bit. And by optimize, I mean, say, make smaller. They grow big if you sort of define things in a naive way, and it's often useful as a post-processing step to say, hi, I would like the machine to be as small as you know how to do. There's some lore about how to do that. The other limitation of the Xerox tools, other than say licensing and obsolescence, is that they don't support weighted machines in general. So the Xerox tools are not useful for sort of like speech applications where everything is a probability. The alternative, which was closed source, if it could even be bought anymore, were the AT&T toolkit, sometimes just called FSM. This was developed in late 80s, early 90s at Bell, and then later at AT&T. Also, it came with another component called LexTools. LexTools is a once again, another sort of domain-specific language that's used to write grammar rules. Like if I actually want to sort of write out regular languages that describe something interesting and convert them to machines, it gives you a handle on how to do that. It's much easier to use Lex tools than it is to sort of build these things from scratch. Once again, very restrictive licensing. It's also written in C, and it abuses the language to an incredible degree. Basically, everything is just magical casts all throughout the library. And there's a lot of things that don't work or are poorly documented. I actually used this when I was an undergrad, and it was a nightmare. Here are some other ones here. I describe in this paper from 2016, I describe what these things are like and how I compare them to tools that I like. First off, there's Carmel. Carmel is developed at the Information Sciences Institute in University of Southern California by a guy named Jonathan Grail. It has that weird DARPA license. I hope I won't offend anyone. It's like you're not allowed to take it to Iran, for instance. Things of that nature. You can't take it to Iran or certain occupied Syrian territories. But it implements many of the classic components you might need. It's a bit inefficient because it doesn't actually have a sort of digital computer readable representation of the machines. It only has a very verbose human readable version. So every operation sort of has to parse and deparse because there's sort of there's no like way to serialize the machine in some kind of compact, useful format. That's a major inefficiency. However, it has many cool things in it. The code is also, I'm sorry to say, completely inscrutable. I've been programming in C++ for many years, and I have no clue how it works. I cannot understand the flow. I don't think it's been written solely by one person without any code review over the course of the last 21 years. So you can imagine the code quality. An interesting, however, it basically has all the functionality you could possibly want, other than it's a little bit slow. Another tool is FOMA, designed by Mons Holden, who's a professor at UC Boulder. FOMA is basically a clone of the XFST tools written from scratch. I tried to use this in a class recently, and I found it buggy. I was able to confirm that machines were not being compiled as per the spec. So for that reason alone, I wouldn't recommend it. It's well written though. There's a bug in something I needed. So we were unable to write. We were trying to write some rules of Polish phonology. They simply didn't get, the machines did not work in a way that we understood. There are two other somewhat obscure alternatives. One is called Cleany. This is by Beasley, again, who also worked on the Xerox tools. Cleany is Java-based, but it's quite advanced, but I think it's been abandoned. Finally, there's a tool called HFST. H is for Helsinki, where it's created. That actually is a very general tool. It has a Python endpoint. You can actually swap in different types of backends from different types of libraries. However, it doesn't seem to have gotten much adoption. So if you're interested in sort of like my slightly biased table of the features of what these things have and don't have and need, you can check out the paper from 2016. Yes, Chris?
Did you also look at SFST?
What's that?
Did you also look at SFST?
I know something called SFST, and I wonder if it's the same one as that you're talking about. I know of a tool called SFST that's by people at Google, Alexander and Riley. Is there a different SFST?
From University of Stuttgart.
Oh, I don't know this. I've never heard of this one. Okay. I assume that also the people I work with who do this hadn't heard of it either, or they wouldn't have named a tool with exactly the same name. I will check that out. Thank you. Here is the base of all the work that I do on FSTs for about the last 10 years. It is called OpenFst, not OpenFst, or also note that the first F is capitalized, but not the ST. That's just the convention. It's a title case. OpenFst is a open source. It's Apache licensed C++ 11 library. It uses relatively modern C++ features. For weighted finite-state transducers. It was developed almost exclusively at Google with occasional contributions from grad students who later came to work at Google, largely. Among other, so if you own a smartphone, I believe that you have some OpenFST running on it. I don't know that for a fact because I can't. See you later, Mark. I can't audit all the pieces that you might be interested in. But speech recognizers are often built on top of OpenFST, using this as sort of the core back end for the decoder graph and decoding. So if you've used the quality toolkit in your research, that's built over the top of OpenFST. Just basically adds the acoustic modeling stuff and sort of orchestrates all the complexities. Many commercial products, I also believe, use OpenFST. I believe Amazon is built in OpenFST. Like Amazon recognizers are built in OpenFST. Android recognizers are built in OpenFST. Who knows about Apple? But
Apple used to have, I don't know what they do now.
they have some papers. They have some papers where they use OpenFST. So I wonder if they also have, use it more widely. Wouldn't surprise me. Speech synthesizers also use these things, not for the acoustic component, but for the so-called front end. So in a speech synthesizer, when we're going from text to speech, or TTS, in that setting, we've got, we do an enormous amount of linguistic pre-processing to take to mark up basically our string into some kind of elaborate, detailed, marked up representation that has like phonemes, and it has intonational curves, and it knows whether the word is pronounced bass or bass, B-A-S-S, whether it's Houston or Houston, all those sorts of complexities. And a lot of those things are handled using OpenFST-based processing. In this case, we sort of, one formalism is simply write grammars that handle things like numbers, dates, times, currency expressions, blah, blah, blah. Write grammars, compile them into finite-state transducers, then use OpenFST to basically do the transduction for us as part of the pre-processing steps. I don't know if it can be reasonably used in the back end. Also, the back ends are sort of moving to neural network stuff. But all the recent interesting neural network work on speech synthesis, the vast majority of it takes not the textual representation, but rather an aggressively marked up thing using language-specific grammars, going to the thousands and thousands of lines of those grammars to actually sort of pre-render the sequence in sort of a linguistic representation that it can then synthesize. So if you've read about WaveNet takes, it's just a back end. It takes a marked up data ready to go with pronunciation handled and things like that. Finally, what's sometimes called input method engines, or IMEs. You know this is basically mobile text entry systems. So what you type on your phone is not what you get, right? Your phone intentionally ignores you in all kinds of interesting and complex ways. It understands that it takes harder to get to the Q key because it's farther away on the screen. It has a so-called spatial model on analog with the acoustic model. Ultimately, also the models that do things like auto-completion, the models that do sort of spelling correction, that handle spacing and punctuation. If you're using a smartphone and you set it to a French locale, that will, if you type ah in the right thing, it'll insert a grave accent versus no accent. Like all those models are ultimately expressed as finite state machines, and like Android mobile text entry systems use OpenFST as the backend. I should mention something about how OpenFST is developed. OpenFST is basically developed internally to Google, and then there's a gigantic Python script that generates the open source version. So basically, you get the same stuff. It's just that there's some like a bunch of munging and removing of special code that uses Google Magic. But basically, everything else is the same. So I use OpenFST. When I'm in Midtown, and when I'm in Chelsea, I use FST. But they're basically very, very similar libraries, and you're not really missing anything of interest. One thing you sort of need to understand to get to the final element of what I talked about this Pynini library is that there's at least 4 layers which you can view OpenFST. And if you're not familiar with C++, some of this maybe won't cohere for you, but don't worry about it. Just know that there are multiple layers you can interact with the system. The first one is a C++ template or header library that lives in fst/.h. So that is sort of like where the algorithms are actually implemented. But that's not usable code by itself. You have to instantiate that code with certain arguments to sort of construct it. You have to tell it what kind of precision, like how many states can there possibly be, for instance. You tell it like, do I want integer level, do I want 32 bits of states? Do I want 2 to the 32 minus 1 states? Or do I want 2 to the 64 minus 1 states, or do I want just 25 states? Maybe I'm doing something really small. I don't know. You can you have full control of these sort of things, but you have to instantiate the code. So that's a pretty substantial barrier to entry if you're not up on your C++ 11 template library coding. There's a much more usable, slightly more user-friendly level called the scripting library. This lives in FST/script, and this actually is instantiated code. This is magic. How it relates to the header layer is that it uses a bunch of cool dynamic dispatch tricks to basically pretend that I've already instantiated a bunch of different types of things. So I've already instantiated all kinds of different levels of precision, different types of weights, different types of disciplines for queues and things like that. It sort of instantiates a lot of the code for me so I have something usable. So that actually compiles into a usable library that you can build against. Many people who have used these tools use the command line interface tools, which are all called, they usually live in user local bin / FST something. So like FST compose, etc. And these just build it up the scripting layer. They need the code to be instantiated, so that's where they work off of. Also working off of the scripting layer is something I wrote when I joined Google called PyWrapFST. That's a Python extension module that links against that scripting layer. And it basically gives you exposure to the basic FST functionality and all the core algorithms that you might want at the cost of basically Python dispatching. It's a relatively compact library. It builds pretty quickly because there's very little code other than the scripting layer itself. It just sort of maps the names in the C++ land onto sensible Python names. It's really very straightforward. Also should mention that OpenFST has all these so-called extensions, which may be interesting to you depending on what you're doing. For instance, there's a library that adds FST compression. This is like a Lempel-Ziv style compression. It understands things about the topologies of the machine. You can make them much smaller. This is very important to us on mobile, where maybe the Russian grammar is a lot bigger than the English grammar for text correction or something like that. That's often the case, that the Russian and Czech ones are like an order of magnitude larger than the English or Spanish ones because of the rich inflectional properties of those languages. We have generic ways to sort of compress the machine that are not just for FSTs, but just will work for any directed graph of any sort. We have an extension that allows you to encode linear models as WFSTs, or a certain subclass of them. There are ones that have finite expansions, and so you can train a discriminative tagger and then encode it as a FST, which can then be sort of mixed into things. And this is very useful for instance, like graphing to phoneme conversion. We have pushdown transducers. Those of you who know formal language theory may be familiar with pushdown transducers. These are the machines that correspond to the context-free grammars. They're called pushdown transducers because they maintain sort of a stack, so that we can enforce balancing of our parentheses, notionally speaking. We actually just build very, very gently over the top of this, over the top of OpenFST. We basically say that here is a machine, which looks like a transducer to you, but some of the arcs are magical arcs that are either pushes or pops on the stack. And I want you to obey that when you expand paths for me. So basically, I just need a special algorithm for shortest path and a special algorithm for compose, and everything else just sort of falls out. Another nice feature which I use quite a bit is I can express basically a context-free grammar as a recursive transition network, for those of you who know what that is. And I can expand it, and it builds the pushdown transducer for me very efficiently. So I can actually write a real context-free grammar and build the machine that corresponds to it. We also have something called the multi-pushdown extension. Multi-pushdown machines are Turing complete, but they have the constrained version we actually use is used to do full copying. We can basically write copy languages over some finite vocabulary in the multi-pushdown transducer world. That's sort of understudied. We don't really know we don't know much about multi-pushdown transducers yet. We may have invented them. Another one that's very useful is we have a way to compress FSTs. Some of you may know what's called Louds compression. Be familiar with this notion. So there's many ways to encode you can encode an n-gram model as an FST. Speaking generally, Louds compression is one way to do this. Is one way to encode a n-gram model also. We can also basically Louds compress an n-gram model and make it tiny and put it on your phone. These are all free to use. some other fancy magic. In addition to epsilons, we also have special magical archetypes, labels like we have rhos, phis, and we have rhos, phis, and sigmas as well. That also is an extension you can use. Built on top of this, sorry, I have a lot of software to tell you about. Built on top of this is a library we call OpenGRM, where GRM is, I guess, short for grammar. Not OpenGrim, though, OpenGRM. Some of the tools in the OpenGRM library are one I wrote, which I need to publish, but it is called Baum-Welch, because it performs Baum-Welch maximum likelihood estimation on certain types of WFST topologies. For instance, you can like train an HMM with this library, among other things. It's a very thin layer of code on top of OpenFST itself. We have command line tools and libraries that allow you to build conventional n-gram language models encoded as WFSTs. That's an incredibly fast and easy to use tool. And if you perhaps use the SRI tools or KenLM, I really think this one is superior. Also, it's incredibly fast. You can build just gigantic models with this tool. We also have something you may have heard of called Thrax. Thrax is a domain-specific language compiler for WFST-based grammar development. So it's sort of like you write very terse regular expression-like grammars, and you can build the FST out of them. Finally, there's something, Chris, here called SFST. That's not the SFST you had in mind, I think, which builds what are called stochastic FSTs, which sort of correspond to, they're like basically things that have an n-gram topology, but we can do very fancy things, like we can take a neural network and then we can have the neural network give us samples that we approximate onto the n-gram topology. So that actually turns out you can do enormous reductions in perplexity by basically using the RNN to generate samples for us, and then transferring them onto a tiny machine that will fit on your phone. All these are available under Apache 2.0 license, and they all use the same binary serialization format as OpenFST. So the way that these tools can talk to each other is like the FSTs that any one of these software pieces generates can be loaded by any other one of the pieces. They all just use the same rather terse binary serialization format, so they all can just talk to each other through the file system, or through strings if you really want to. So that makes these things relatively like sort of pluggable. You can build very nice little things using a bit of Bash and a bit of Python. The tool I'd like to show you, though, shortly is called Pynini. And Pynini is one additional layer on top of all these other things. So I mentioned here that we have a Python extension module called PyWrapFST. Pynini is just one more layer of a bit more Python extension module that adds all the sort of grammar compilation functionality that's not built into the core library itself. So two key things it adds is the ability to build rewrite rules, which correspond to like phonological rules, and secondly, a generic routine to optimize arbitrary FSTs, which I'll talk about both briefly here. Here are some conventions of the library that sort of all these tools share. FSTs, and also this FST and symbol table objects. We also have a notion of like a symbol table that maps labels onto words, if we want to. They implement what's sometimes called cow semantics, or copy on write. So if you actually copy an FST, you don't actually do anything other than incremental reference count. So any copy method or copy constructor in the library makes a shallow copy in its constant time. It literally just increments an integer. That's all it does. So you can make so you can just write kind of crazy, very inefficient looking code that actually is quite efficient. It's only when the machine is mutated that we actually have to make a deep copy. We have a bunch of iterators, and they're of course invalidated by mutation operations. Another convention that's really sort of novel to this library is we assume that everything is a weighted transducer, even if there's no interesting weights. Every weight is just one, notionally speaking. And also, an acceptor is just a machine where it just happens that the input labels and the output labels just happen to match. It's just a coincidence in our world that that's the case. We have each state is actually just an integer, and they have to start at 0. We also have exactly one state as a start state, and if we actually want to say that we can actually build a machine that's truly empty, and the way we do that is we say the start state is -1. If you want to symbolize like a truly empty machine, the empty string machine, for instance. We also have each one of these transitions is labeled with an integer, which has to be non-negative. By convention, 0 is reserved for epsilon. So you can't use 0 yourself. It just means epsilon. It's a sort of special transition label that doesn't match anything. And negative integers are reserved for implementation, so you sort of just can't safely use negative integers even if you want to. So just don't. Every state in the machine is also associated with a final weight. So if you actually want to say that a state is non-final, you associate it with an infinite weight, which we write bar 0. That's right here. This is bar 0. And then any final state just has some kind of non-bar 0 weight. And you sort of add, you just multiply that weight onto the end of the cost of the path, as it were. These are all sort of library conventions, and other libraries have different conventions. Inside of Pynini, there's one more handful of conventions inside of this extension module itself. Some FST algorithms you want to apply are inherently constructive, by which I mean that like you give them one or more FSTs, and they make you a new FST from scratch, sort of piece by piece. Those are what I mean by a constructive algorithm. Others are naturally expressed as destructive algorithms, meaning that you give it an FST and perhaps others, and it mutates that FST in some way. That usually like doesn't do a relatively minor change to the topology. Usually what it does actually is it adds or removes arcs or states in the machine. Many of these constructive algorithms are constructive because they're actually implemented, you might say, on the fly or lazily. So the implementation is actually like, it builds the machine state by state, and you can actually say like, build me the next state, build me the next state, with a cache in the back end. So if you actually want to sort of expand the whole machine at once, we sort of just say is, don't cache because you won't be returning to that state again. Just build the whole machine at once and pack it into a new coherent container. And not all algorithms can be implemented this way, and conversely, some algorithms, we only know how to implement them this way, more or less. We don't have a non-on-the-fly version. So the way we turn that C++ convention into Python is the following. If the algorithm is constructive, then it's sort of a module level function. It's just Pynini dot whatever, and that takes FST arguments, and it builds me a new FST and gives it back to me. It handles, of course, all the memory management and such. Destructive algorithms, the ones that actually mutate the FST, are implemented as instance methods, and of course they just sort of mutate the instance they're invoked on. So, for instance, there's an algorithm called connect, which removes non-accessible and non-coaccessible states. That just walks through the machine, finds states that can't be visited from any other state, and deletes them. That's implemented as a instance method. Also, because this is like some of these sort of doing this destructive stuff in place is a little bit weird for Python programmers, I find. Where possible, these things also return a reference to self, so you can chain them. So I can call .connect, remove epsilon, so on and so forth, all on one object, and that will generally speaking work. Also, occasionally you want to use the destructive algorithm constructively, so we just have a little syntactic shim for that. There's also, so for everything that I can use destructively, there's a version that's at the module level as a function, which just makes a copy, does the mutation, and gives you back the copy. And handles all, once again, handles all the reference counting and things of that nature for you. So let's talk about a couple algorithms, what they look like in this land. These are just sort of classics. Obviously, the set of supported algorithms is about 40, most of which I have never had an occasion to use. I still have never reweighted a machine. I know what it does, but I don't know why you'd want to. So let's talk about a handful of classic ones, including the ones I discussed earlier in the set section. So the concatenation of two machines A, B can either be computed destructively on A by saying A dot concat B, where A and B are FSTs. That just works. And what that will mean is that I actually sort of will concatenate B onto A. A will be mutated. B will be kept clean. B will not be changed at all. Or I can do it constructively using just I've overloaded the plus operator in Python. I can't just write AB. That won't Python. That's not syntactically valid. You can't just put two identifiers next to each other in Python. So I have to say A plus B. To give you an intuition of how the algorithm works, it's actually pretty simple. This is the so-called Thompson construction. This is Ken Thompson, who built grep, among other things. He sort of wrote about many of these algorithms, sort of the obvious ones. So what you do is you add an epsilon arc from every final state in A to the initial state in B. It's really the whole algorithm. You just need to find every final state and then basically make it transition to the initial state. That's really the whole story. Many algorithms can be sort of defined in those sort of terms. Another one is union, which I traditionally write A pipe B. This can be computed destructively on A using A dot union B. So once again, B is left safe, A is mutated. Or you can do it constructively saying A pipe B. I'm allowed to overload the pipe operator in Python. It's a binary infix operator that's supposed to mean it's supposed to mean some kind of logical union. And in fact, well, this meets the test here, right? This is a logical union. The algorithm, once again, basically just does little epsilon arc hacks. It finds the initial state of A, and then it adds an epsilon arc to the initial state of B. Once again, very straightforward. One thing to note about these, almost all these little core algorithms introduce epsilons, which are often, strictly speaking, not necessary and can be removed at a later date. So we'll talk about that in a second. Another key algorithm is closure, so A star. I can't make star a postfix unary operator in Python, sadly. The grammar of Python won't allow that, so I have to just make it a method. So it's A dot closure. That's the destructive one. Or I can say, there's a stupid typo here. Sorry, I will clear that out. The algorithm introduces epsilon arcs from all final states to the initial state. Once again, you find all the final states and you just map them back to the initial state. That's how you get a cycle in the machine. Pretty straightforward. Finally, we have the algorithm known as composition. Sometimes written as A circle B. Composition is how we chain two FSTs or FSAs. Composition if you have two FSAs, the composition of them is just their logical intersection. It intersects all the strings that they match. If we have an FSA and an FST, it sort of runs the FSA through the FST's transduction and gives us the output. If we have two FSTs, it's like chaining two transductions. This is really powerful because after I've chained a bunch of transductions together, I can apply a generic optimization routine and basically remove all the redundancy in those rules, sort of as if by magic. And in Python 3 onward, I can overload this. And the way I overload this is I can say A at B. That's the at character. In Python, that's supposed to be the dot product. And actually, there is a sense in which this is sort of like doing a dot product in the string space. That's not completely crazy, because it's sort of a logical intersection. It's thinking of it as doing a Boolean dot product over what strings are in and out. Or you can say compose A, B. By default, states which, so by default, the composition algorithm generates a bunch of states which can't be reached along valid paths. So a state is said to be accessible if you can reach it from the start state by valid transitions that are allowed by delta. It's said to be co-accessible if from that state you can get to a final state via valid transitions. So a state which is not accessible and a state which is not co-accessible, they're redundant. They don't do any good for us. By default, if you call A at B or compose A comma B, what happens is it just trims those states for you. And a machine so trimmed is called trim, traditionally, or connected. That just happens in the back end for you magically. You can disable that, but it's only really useful to disable to debug. You can sort of see where your composition went bad. Other than that, it just magically sort of trims that behind the scenes for you. So you'll get a trim machine out of composition. This is how we use to sort of like run strings through rules, or to combine a bunch of rules together into a rule cascade like in phonology. One last one here is I have the cross product operator. In Pynini, this function is just called transducer for historical reasons. It constructively computes the cross product transducer T, where T is A cross product B. So this is sort of used like if I wanted to say like A goes to B, I can just build the machine using the transducer function. Here I've given a little bad Python snippet of how you do it. If you were just building it from scratch. Don't use this one, just use the transducer. I think it's much cleverer. I've given it with an underscore because I don't actually want you to use it. But here's how the algorithm works. It's actually very simple. This goes through and it deletes all of the output labels on this on the first machine. That is to say, it turns all the output labels to epsilon. So it sort of makes this a machine that maps to nothing, maps from a bunch of strings to nothing. Then this does the same on the input side. And then if I just compose the two and remove all the resulting epsilons, I get the cross product machine. This is just a little bit magic that makes it go fast. So this is basically how you'd implement this if we didn't already have it built into the library at a lower level. And so that's probably the best possible way to actually sort of build a cross product from a set of strings. One thing about almost all these operations is in Pynini, you don't actually need to pre-compile the FST. You can just pass a string and it will coerce it to an FST for you, sort of doing the obvious thing. It'll build the obvious sort of string machine version of what you do. So you can just insert strings in almost every place and you'll get the right behavior. I'll have an example of that in a minute. See, one or two last algorithms here. By the way, how much time do I have?
I think, actually, I was just going to say maybe, can you wrap up in about 5 minutes?
I can do that, sure. Sure.
We can maybe have a few questions, but I know we have meetings and stuff.
Great, great. I will do that, right? This is one last point of interest here I should mention. So an FST is sometimes said to be optimal if it is minimal. And by minimal, I mean it is the smallest FST that could possibly do what it's supposed to do. Minimization algorithms, both the classic and the modern ones, require that their inputs also be deterministic, which means that that we only can have one transition with each label from a state. In Pynini, FST objects have a built-in method called optimize, which applies a generic routine for optimization. Here's how it works. This is a very simple version of it for unweighted acceptors. We first sort of compute the properties of the machine. We ask whether it has epsilons, and we ask whether it's already deterministic. That's all these first 3 lines do here. If there are epsilons, this is how we check the properties here. It's kind of annoying syntax. If there are epsilons, we remove them. If the machine is not deterministic, we determinize it. Determinize is so I should mention here, rm epsilon works in place. It's a destructive operation, so it's a method. Determinize is constructive, so we have to sort of copy over the top. This is valid, by the way, because Python execution order is well defined. The right-hand side executes before the assignment. So this can't like cause weird memory seg faults or something like that. You're allowed to do this in Python. In C, not so much, but. Then finally, we minimize the machine having determinized it. This will produce an optimal FSA for any machine that happens to be a so-called acyclic acceptor over a so-called idempotent semiring, of which most are. However, some weighted cyclic FSAs are not determinizable, well-known result. The hack we use is we determinize and minimize the FSA as if it was unweighted. This doesn't actually give us a minimal machine, or it's not guaranteed to at least. But it usually makes the machine orders of magnitude smaller. Similarly, not all transducers are determinizable. This is a well-known result. In fact, we don't even have a positive characterization of what makes things undeterminizable. We just know that sometimes the algorithm doesn't terminate. Instead, we determinize and minimize the FST as if it was unweighted and an acceptor. Once again, it doesn't guarantee any optimality in any meaningful sense, but in practice, it makes the machines much smaller, like 99% of the time. This is sort of an open problem about how to do this in general, and I don't think this is ever going to be a general solution. This is sort of our well-documented solution. Another thing we have is very, very nice is we have the context-dependent rewrite rule compilation function called CD rewrite, which constructively turns an SPE, like sound pattern of English, Chomsky and Halley style phonological rule, like A goes to B between C and D, into a transducer. We use the so-called Moore-Insport algorithm, which is actually provably correct, unlike the Kaplan and K one, which is full of errors. I'll skip over a couple things here. I want to jump to an example really fast before I run out of time. Here's a simple example. I tried, on the train today, I wrote Latin American mainland Spanish grapheme to phoneme conversion rules, just working from my memory. And here, I'm going to skip over to that here. And I want to show you a little bit what things might look like in Python here. Let's make that go away. There we are. So here, I'm just going to use a star import. It's star import safe. I try to not give anything crazy names. Just keep the rules short here. Here's what a context-dependent rewrite rule looks like. If I want to say, so tau is a transducer in my setting, that sort of, like I can say A goes to B. But if I want this rule to apply over an arbitrary vocabulary, I have to embed it in a vocabulary which we'll call sigma. Sigma is the closure over the alphabet of the language. And then I usually optimize it using this generic optimization routine. Here's a variant of this that also takes a right context, which I'll need in Spanish. So this actually says like A goes to B, that's tau, when followed by the following strings on the right-hand side. And once again, it optimizes that. I put these little pieces in there. Here's some stuff I built here. I need front and back vowels in Spanish. And then I can compute their union here, which I've called PHV, PH as in phonemic side. And then here are also vowels that appear in written Spanish. This is like the ones with the acute accents, for instance. But you don't need them otherwise. This is, of course, I'm not going to claim this is complete. Like I think I need oo with the diathesis, for instance, for words like guel and things like that. Here's a list of phonemic consonants in Spanish, in a sort of a mainstream Latin American mainland dialect. And here's a couple ones that only appear on the written side but are never on the pronounced side. So C is never the palatal fricative in English. And similarly, H is silent, right? There's no H phoneme in Spanish. And then finally, I construct a sigma, which is the closure over the alphabet. And I compute the closure and optimize that. That's necessary because we have to use that to compute the context-dependent rewrite rule. We basically need to tell it what is it allowed to pass through, in addition to what is it required to map. So let me just show you a couple of rules here that I've built. I have a list of sort of like, how do the digraphs handled? Well, cha is cha in Spanish. Double L is a hia, something like that, depending on where you are in the Latin American world. And QU is just K, always. It's always hard. Got to remove the accents. And the thing written with a V is usually just pronounced as a B in much of Latin American world. And I mapped the enye onto the actual palatal nasal here. I have some complicated rules here to handle how R's work in Spanish. And actually, I know they're not quite right because the rules are much more complicated than I've given you here. The basic idea is that double R is always trilled, and single R is always flapped. But the trill is written with an R. So I have to map the double R onto a magical capital R, map the single R onto the flap, then map the capital R back onto R. This is the kind of thing you have to do when you write these rules all the time. This is a very common problem that comes up. And I actually, every time here, I'm actually just composing these rules together. I'm chaining them, and they apply in order, as if they were ordered rules. I have some rules here to handle a bunch of these different back consonants here. Here's also all the rules that handle G and C and so on and so forth. So this, for instance, says that G is pronounced as ch when followed by a front vowel, which is A or E. The vowel is pronounced A or E, which is a true statement about Spanish. I then chain all these rules together and optimize them. And I call that G to P. And I'll post a link to this here when I post the slides if you're interested. Then here's a little simple function that just helps me compose it and extract the shortest path, so I can get the string out again. This is just does a rewrite for me. Depending on how complicated the rules are, you can use more complicated functions. This is a very basic one. So here's the example. I'm going to apply this. I have the word cuando, and these all work, by the way. So I was able to do this in about 30 minutes and get it working. So cuando comes out as cuando. This is yerba, hacer, llave, and perro. I'm sure that there are many deficiencies here. I know that my allophone rules aren't quite right, and so on and so forth. But it gives you a sense of how you can write these things very quickly. I think at that point, I'd like to just jump back to this future reading here. I had an example of how I would do this in sort of a machine-learned fashion using the same tools. I'll post this link if you're really interested. I'll skip here because I'm sort of out of time. Let me tell you how we use this stuff. Some things you might want to read. In Gorman and Sproat, we propose an algorithm implemented in Pynini which can induce number grammars from a few hundred labeled examples. So you tell me, how do you say 23 in your language? How do you say 74? And I can basically build a grammar that maybe goes up to 1 billion from maybe 100 or 200 examples. We express this as basically a bunch of rewrite rules. We can sort of generalize from the data. Recent paper in Interspeech by Sandy Ritchie and some of my colleagues described how Pynini is used to build so-called unified verbalization grammars. And when I say unified, I mean that we actually can share them across speech recognition, where we have one-to-many, and TTS, where we have sort of one-to-one. We can pronounce numbers and dates and times and all these things with sort of one grammar, many uses. We also describe how these things can be used to constrain sequence-to-sequence models, either linear models or RNN-based models in some recent work. This is all from my team at Google. Finally, if you're interested in learning more about this, let me suggest a couple things. If you need a backing on stress and strings, the book by Partee et al., the first 3 chapters, is very easy to read, easy to find book. It's called Mathematical Linguistics or something of that nature. The papers by Mori, including the 1997 and 2009 one, are both free and they're absolutely classic and will give you a very good background. If you want composition to go faster, I have a recommendation there. If you're interested in sort of how we do decoding, shortest distance and path problems, read the Mori 2002 paper, wonderfully written paper as well. Of course, we have a website for Pynini itself. It has all the information about its installation. And here's some of the sort of more software built on top of it that you might be interested in. Not all of these links work quite yet because I haven't got licensing set up for all of them, but they all will work within the month or so. Thank you so much.
We have time for a few questions if anyone would like to follow up on anything Kyle has said. Any questions?
So you've gone through a lot of implementation and stuff.
Grab the microphone there.
Yeah, thanks. You've gone through, Kyle, a lot of different implementations, finishing with Pynini. Is that what you recommend as kind of the starting point for entry into this constellation of tools?
I think so. I think it's a good entry point. So one thing that, like, you know, I could, if I had even more time, I could show you is that how hard it is to say, like, build a string machine. Like, you give me a string, and I make the machine that accepts just that string and nothing else. Surprisingly hard to do at the low levels. It's about 20 to 40 lines of C++, whereas it's, you know, simple built-in command at the Pynini level. So if you're working with string systems, you know, you're working with strings or words, it's sort of the best place to start. If you want to build a speech recognizer, you could do it, but it'd be miserable as a tool to sort of like build a speech recognizer. There's just too many inefficiencies. So if you want to build novel speech technologies that you do acoustic modeling, things like that, it's a bad place to enter. But for just about everything else, I'd say it's a great place to enter.
And then you also earlier on mentioned this set of command line tools. I don't remember how full that implementation was, which would presumably remove the need to work within a specific framework like Python. But I wonder whether it's a complete implementation and a possible way to start if you're not trying to embed within Python code. I think no. The problem with those tools is that once again they don't have a way to compile a string or anything like that. You sort of have to. So you have to do the only way you can communicate it with it is that you either build human-readable arc lists, like lists of the actual transitions, in a classic so-called AT&T format, or you build the serialized things that you've built for the other tools. And you can sort of compile and print between those two things, but that's basically all you can do. But if, say I want to go and take every state in the machine and make it final, and for every transition, if a transition goes from A to B at state I want to also add all of the I want to add the row transitions, all the transitions that are in the alphabet that are not that one as self transitions. Like it's a common thing I want to do. That's like a complementation operation. That's incredibly non-trivial if you have to work with the arc lists and you have to work with the things, but it's trivial in Python.
Like the command line stuff is great if you just want to compose a couple of compiled transducers you already have, like you have a lexicon transducer and you have language models and other stuff. But you know, yeah, you have to construct the damn things yourself.
Yeah. So like I do use those tools. Don't get me wrong, but like a common workflow is I have like a Python that does a bunch of Python code that sort of builds all the things. And then maybe in the middleware, I might have a bash script that does some more stuff, and it uses these tools when the things I want to do can be expressed as those tools. And then I maybe go back to Python. Like another thing that's sort of completely missing is sort of like a rewriter or a decoder type operation. I can compute the shortest path, but to turn that back into a string, there's no way to do that from the command line. You have to write your own. So I think that honestly, the barrier to entry in the C++ land is very high. And I think like this is the first tool to really bridge that in OpenFst land. I'm surprised to hear that a lot of people are using this in places that I wouldn't expected. You know, I know Dan Roth's lab used it as an EMNLP paper. This I just saw. They use it to basically do constrained decoding sort of things. I was surprised to hear that they found it useful, but I'm really happy.
Any other questions? Okay, well, thanks a lot, Kyle.
Thank you.
Thank you.